Hi, I'm Zor. Welcome to Zor Education. Continuing talking about graphs, I would like to devote this particular lecture to a completely different way of graphing dependency between two variables on the plane. We used to have rectangular or Cartesian, as they're called sometimes, coordinates on the plane. So you have one axis, which is x-axis, another perpendicular to it, y-axis. Both are linear dimensions, basically. They are represented, the points where any number is basically represented by a certain point on this axis and point on this axis, and something like dependency which you have is a set of all points x, y on this particular plane, where x is projection to the x-axis and y is projection to the y-axis, and this particular equation is satisfied. So this is the rectangular or Cartesian system of coordinates. Now, I would like to introduce a completely different approach to represent a point. Here it is. Let's just assume that the position on the plane is not defined by a relative position to two perpendicular axes, but you have only one axis, and it's not really an axis, it's a ray. I mean, it can be called an axis, but it's only half line. Now, every position on the plane can be characterized by two things. Let's draw this particular vector to this point. So, this is called O, this point O. This is called polar axis. This I'm not sure, but it can be called as a polar vector if you wish. And this angle can be called polar angle. Now, position of this point is defined by how much this particular vector in angular dimensions is rotated from this position along the polar axis. So if you take this particular direction, how much do you have to turn to get to this particular direction? Now, obviously, for any point on the plane, there is this particular angle, which is basically from 0 to 360 degrees, or from 0 to 2 pi in radians, and the angle defines direction towards the point. Now, how far this point is from the center is a second variable which we need, which is basically the distance from the center. So two things. We have a distance from the center, which is usually denoted by letter R, and the angle from the polar axis, angle of the vector towards our point from the polar axis. It's usually denoted by letters either phi or theta. I'll use probably phi, doesn't really matter. In my notes, I think I'm using theta. Both are equally acceptable. Obviously, you can use anything, but this is tradition, let's put it this way. The R and phi, or R and theta, are traditionally for these two things. So, knowing these two variables is sufficient to determine the position of the point on the plane. So, instead of two perpendicular x-axis and y-axis, we are using the polar axis, but there are still two different variables which we need to determine the position of any point relative to the polar axis. So, let's just give a couple of examples. What would be coordinate of this point on the polar axis itself on the distance, let's say, a? Well, coordinates would be r is equal to a and phi is equal to 0, right? Since we are on this polar axis, we don't have to move. That's why phi is equal to 0. And the distance we have to move from the pole itself is equal to the a, as I was just saying. So r is equal to a and phi is equal to 0. So coordinates at this point are a, 0. Okay, how about this point? Well, I shouldn't say minus. I'm talking about distance, so this is also distance a. So the continuation of the polar axis to the left from the pole to the opposite direction. I shouldn't again say left because there is no left and right. This is the positive direction and that's the only we have. So I'm going to the negative direction against the direction of the polar axis. Also on the distance a. So what would be coordinates of this particular point? Well, again, the distance is still a. How about the angle? Well, from this position, we have to turn to this. So it's 180 degrees, or usually it's in radians, which is pi. By the way, I'm using radians, angles, and other vectors and other terminology here. Well, obviously you understand that we are talking about graphs. We are talking about something which is in the middle between algebra and geometry. So that's why I'm using, for instance, the radian measure of the angle. If you're not familiar with this, you just have to go to a geometry lecture where I explain what actually radian measure of the angle is. So I will use it basically as it is a known term. And hopefully you do know. If you don't, there is a reference, the same unizor.com contains the lecture about the angles and how they are supposed to be measured. All right, so as I was saying, coordinates of this point are same a. Note, this is a distance which is always positive. There is no negative direction on this particular axis. This is only one positive direction. So everything else is achieved through turning, in this case, by pi. So that's coordinates of this. How about perpendicular also on the distance a? Well, let's think about it. The distance again is a. And what's the angle? Angle is 90 degrees or half of the pi. So this is a pi over 2. And on this side, if it's also distance a, same thing. R is equal to a, phi is equal to, well, we can actually turn 3/4 of the full circle, but this is not again traditional measurements. Traditional measurements is going to the opposite direction by a quarter of a circle. So anything which is on this half of the plane is usually measured in a negative value of the angle, because the positive value is counterclockwise, as we know. Again, that's the geometry. Measure of the angle is always positive when you're moving to the counterclockwise direction. Moving from here to here is clockwise, and that's why it's negative. So the coordinate of this particular is, again, r is equal to a and phi is equal to minus p over 2. So that's the coordinates of this line, of this point. And, you know, if it's something like on a bisector of this angle at 45 degrees or p over 4, it will be correspondingly a and p over 4, etc. So this is how the polar system of coordinates is built. Again, we have the angle and we have the distance from the origin, from the pole. Well, let's do a couple of examples here. Well, example number 1 is r is equal to a. Is this a function? I mean, remember, the function, I'm not using x and y anymore. The function would be described as this. And again, I shouldn't really say a function. A dependency between r and phi is expressed in this particular way. Is this an example of this dependency? Yes, absolutely. It means phi can be anything. So no matter what it is, but r minus a is equal to 0, because that's what it is. This is our function. So for any phi, for any angle, any point which is distanced from the pole by a would satisfy our equation. Now, obviously a should be greater or equal to 0, because r is a distance, right? So only equation of this type, or this type, where a is non-negative, makes sense. So let's draw the graph of this particular equation. Well, this is our pole. This is our polar axis. And what we are saying is that any point on a distance a, which is this point, this point, this point, regardless of the angle, this angle or this angle, doesn't really matter. So regardless of the angle, any point which is distanced by a from the pole would lie on the graph of this particular equation. So what is it? Well, obviously this is a circle. So this is an equation of the circle in polar coordinates. Now, recall that the equation of the circle in Cartesian coordinates is x squared plus y squared is equal to r squared. A little bit more complex, right, than this one. So, circle is much more simply represented in the polar coordinates than in Cartesian. Well, another example. By the way, this is a circle with a center coinciding with the pole itself of the polar coordinate system. If center is not coinciding, the equation is much more complex. But let's not go into this. We're talking about just very simple things. Now, how about straight line which is going through the pole? Well, let's just consider any point on this line has exactly the same angle phi, right? In this particular case. Any point on this piece of the line, this is the same angle plus pi, plus 180 degree, right? So, it's a combination of two pieces. One piece is determined by phi is equal to, let's say, alpha. This is an angle alpha. And I presume that alpha is from 0 to pi. And this piece is phi is equal to alpha plus pi. So union of these two graphs, basically, union of these two graphs, represents the whole line. I mean, this one represents half of the line, and this one represents another half of the line. So how to unionize? Well, the previous lecture I was talking that to unionize two different graphs. You can use, for instance, the product equal to 0, right? So phi minus alpha times phi minus alpha minus pi equals to 0. This might be an equation of the line. R is not part of this. R doesn't depend on R. It depends on the phi. So the phi can be either equal to alpha or equal to alpha plus pi. So for any alpha within this range, that's true. All right, and the last example which I wanted to present is this. A spiral. How can I draw a spiral? Well, I'm talking about right now the spiral which is called Archimedean spiral for Greek mathematician Archimed, I don't know how to pronounce it. Well, in any case, as you see, I am starting in the beginning. So when my phi is equal to 0, my r is equal to 0. Then as phi increasing, my r is also increasing. So as I move my vector this way, I'm moving away from the center, from the pole. And that's what actually makes the spiral. Now, whenever I make a one circle, in this particular case, phi is equal to basically 360 degrees, right? 2 pi. So if I have an equation which looks like this, what does it mean? Well, again, if phi is equal to 0, r is equal to 0, then my phi increasing, my angle increasing, so I'm going this way, and my r is increasing by the same thing. Now, by the end of one circle, my phi is equal to 2 pi, right? One circle, 360 degrees. So this particular segment is equal to 2 pi in lengths. But then I can increase phi even further. Now, when it goes to second rotation, I will have point here, which is 4 pi now. 2 pi, and again 2 pi, etc., etc. So it's growing this way. This is how the spiral actually is increasing in radius. So it's called the Archimedean spiral. we can actually have it a little bit more complicated. Instead of just plain r is equal to phi, let's see what happens if I have a slightly more interesting equation. If I have a linear dependency, r is equal to a plus b phi. What's this? Well, let's think about it. Let's just draw this. We start again from our polar axis. So at phi is equal to 0, my r is equal to 8. So 8 should be greater or 0. So this is 8. Okay? Now, let's consider that b is positive. So, as phi is increasing, r is also increasing. So, it will be further. So, if I will draw, let me just get a little bit smaller scale here. What if a is here? This is a. Okay? So, if I will start from this, this is the point with phi is equal to 0, r is equal to a. Now, my increasing phi, if b is greater than 0, I'm moving further from a. So, if this is my circle of the radius a, my point would be further from this circle and further and further and further again and again. So I will increase the radius for positive b as phi is increasing. If b is negative, what's interesting is then as phi is increasing, I'm subtracting basically something from a. So instead of going outside of this circle of the radius a, I'm going inside, so it goes this way. Closer and closer and closer to 0. And at some point, I will reach r is equal to 0 when phi is equal to, if this is 0, so it's minus a over b. Right? So if b is negative, a is positive, so that's why it's a positive value. It's minus and b is negative, so it's positive altogether. But this is the maximum value of phi which I can afford, because at this particular value r is equal to 0, and my graph goes to the center of the pole, and there is nowhere else to go. R cannot be negative. R cannot be negative. So for a negative b, my spiral is going inside and basically going tighter and tighter around 0, around point 0, and finally it does reach in a finite, actually, number of rotations. If b is positive, it goes outside of the circle bigger and bigger and bigger, and that's to infinity. All right, so that's basically what the spiral is, the Archimedean spiral is. It's just an interesting example of how simple certain very complicated curve, and this spiral is a complicated curve, how simple it can be expressed in polar coordinates. Something which is simple in Cartesian coordinates, like for instance the equation for the line. It's just a linear function between x and y, is a little bit more complex in the polar coordinate. I have to basically combine two pieces together, etc. And vice versa, something which is simple in polar coordinate, like for instance Archimedean spiral, is a very difficult curve in the Cartesian coordinates. So that's why people are using both at certain, different cases. By the way, speaking about polar coordinates and its usage, actually there is an equivalent in a three-dimensional space. We are using, as you know, the longitude and latitude on the surface of the Earth. Basically, these are spherical coordinates, which is kind of an extension of the polar coordinates to three-dimensional space on a sphere. All right, so what's next is we would like to see how polar coordinates are related to Cartesian coordinates in some simple case. Well, let's consider you have Cartesian coordinates and polar coordinate, which is with the polar axis coinciding with x-axis, because that's the simplest way, right? So the polar coordinates are on the same plane. This beginning of the Cartesian coordinates is the pole, and the positive direction of the x-axis is the polar axis. And now I have a point which has, on one hand, coordinates r and phi in a polar coordinate system, and x and y in the Cartesian coordinate system. The same point on the plane. Now, my task is to express one set of coordinates through the other. Well, now, again, we're talking about graphs, so it's between geometry and algebra. In this case, it's trigonometry, which is kind of extension of geometry towards algebra. So I will use trigonometry, and again, I will use it as is. I would basically urge you to go to the corresponding lectures or whatever the educational material you have to learn about it, but I will use trigonometry as given. So let's just drop the perpendicular here. Now this is x and this is y, right? Because the coordinates are x, y in Cartesian system. Now this is r and this is phi. So let's just consider this particular picture. How to express, let's say, x, y in terms of r and phi? Well, that's easy, because x is equal to r cosine of phi, and y is equal to r sine of phi. Basically, it's from the definition of the sine and cosine, almost. Now, how to do it in reverse? How to find out what my r and phi are if we know x and y? Well, r is easy, because this is the Pythagorean theorem, right? So since r squared is equal to x squared plus y squared, r is equal to square root of this. Arithmetic square root, positive value, x squared and y squared are also positive, so it's always correctly defined, regardless whether the point is here or here or here or here. With the phi is a little bit more difficult. Here is why. Basically, from the definition of tangents, which is another function of trigonometry, tangent of phi is equal to y over x. This is practically from the definition, almost. At least for the phi within the range from 0 to 90 degree to p over 2, that's basically true. So from this, we can always find phi using an inverse function called arctan. So this is, I would say, the beginning of the process of expressing r and phi. Well, actually phi. R we have already finished, the phi. Because now we have some problems. First of all, in this particular case, x cannot be equal to 0, right? So what if x is equal to 0? But let's just think about this. X is equal to 0 is a special case. It means all the points where x is equal to 0 are here, right? So, for all these points, phi is either equal to pi over 2, 90 degree, or minus pi over 2, minus 90 degree, right? If point is here, it's 90 degree, pi over 2. If point is in this particular part of the y-axis, the angle phi is equal to minus p over 2. So I can actually consider all these cases. So if x is equal to 0, if y is equal to greater or equal to 0, then phi is equal to pi over 2. If y is less than 0, then phi is equal to minus pi over 2. So we have finished with x is equal to 0. Now we can define, we can divide y over x whenever we want to, and we will have no problems. Case x is equal to 0, we finished. Now, what if x is now greater than 0 or less than 0 in this particular part or in that particular part? Well, if x is in this particular part, then it's easy. It's only one case. And we can say this formula actually is correct. Arctan y over x. Now, why is it correct? If y is also positive, then it would be positive value, and we will have the positive value of phi from 0 to pi over 2. If y is negative, the result would be symmetrical but with a minus sign. And that actually corresponds exactly to this picture. So if x is less than 0, that actually presents a little problem. If less than 0, it means it's here. So the points are either here or here. But let's think about it. If point is here, then this angle is the same as this angle plus pi, right? So I can always say that if y is positive or 0, then my phi is equal to arctan y over x plus pi. And finally, if x is less than 0 and y is also less than 0, so it's somewhere here, I can always say that this is the same as this plus pi. We have to go negative pi. From this point, we go backwards, because all these guys have negative phi. So it's equal to the same arctan y over x minus phi. So it might actually look a little complicated, but this is the main thing. So as soon as you have defined it for the first quadrant, of the coordinate plane. Everything else is just basically mechanics. But the problem is that you have to know a little bit trigonometry to convert one to another. Well, basically that's it. I mean, if you know just a little bit of trigonometry, then the conversion would be very easy. So this is conversion from polar to Cartesian, and this is a conversion from Cartesian to polar. R is very simple, but phi is, it depends, considering many different cases. All right, so basically this is all I wanted to talk about the polar system of coordinates. Again, as I was saying, under certain circumstances, polar coordinates are more convenient than the Cartesian. However, I should really say that Cartesian are much more often used in study of mathematics. But it's interesting, you know, some very nice curves like Archimedean curve can be expressed, spiral can be expressed in this particular way. All right, thank you very much and good luck.